Hey guys, welcome to linear algebra. We will start something new today. Unfortunately, as you have seen in my email, I tried to record a lecture last night by myself. That was a big mistake. Since I didn't have any confirmation that somebody can hear me or something like this, I think somebody has its mic on. So since I didn't have any, I didn't know exactly what happened. The video doesn't have any sound, so I will not upload it on YouTube, or maybe I don't know. We'll see what I will do. Maybe I'll try to record another one. The notes are already written, so probably it will go faster or something like this. Anyway, I think I will do it today, and I might send you the, who knows, maybe perhaps after this lecture, we'll see. Anyway, I'll send you an email about it. Okay, so now let's get started. Like I said, we start something new. We will talk about chapter number 5, linear transformations. We have 2 more chapters to go on this intensive summer course. This is a very important chapter. Here you will see we will make connections with everything that we have seen so far with the first 4 chapters, and even when we will do the next chapter, when we will talk about the eigenvalues, say the eigenvectors, you will see that it will be connected to this chapter as well. All right, so let's start with the introduction. By the way, one more thing I want to add. I sent you some notes. Those notes are not updated. I will update the lecture notes. And probably sometime around this week, and I'll send you the link with the updated version of the notes for this chapter. Okay, now in this chapter, linear transformations, so I'm interested in, so let's talk about introduction to linear transformations. One more thing, I want to make sure everybody hears me well, perfectly, right? So there is no problem, correct?
Yes, we can hear you.
Yeah.
Okay, that's great. I just want to make sure. When you don't hear anything from me, or you by some miracle, please just say so. Okay. We're interested here, in the first place, we're interested in finding the image or the pre-image of a linear transformation. We will see what that means. Also, we were interested to see whether a function is not a linear transformation. And also, we're interested to find a linear transformation. So these are the main goals for today's lecture. So we will start with images and pre-images of functions. I want to say a few words about this. So in this chapter, we will learn something about functions that map a vector space into another vector space. So let's say we are interested in functions which map, this is a very important notion, map a vector space into another vector space. In other words, this type of function will be denoted by t, let's say, for transformation. It's just a notation. You can use any other notation. So t, which will go from v to w. So this is what we will call a map from one vector space to another vector space. So, for instance, V will be considered, once we have this map T, or this function T, V will be considered, let's say the first vector space will be considered the domain. So this guy is the domain. And this is the codomain, right? And this is our function. So T goes from a vector space to another vector space. And now, if, well, of course, we can send elements from one vector, from V to W. So if V, let's say an element V is in V, my vector space V, and W is in W, such that T of V equals W. So just like I said, we will send one element from the domain to an element from the codomain. Then we say that W is the image of V, is the image of T. Sorry, the image of V. The image of V under my function T, under T. That's what it is. So W is the image of V that was sent through my function T. Okay? And now the set of all images of vectors in V is what we will call is called the range of T. The range of T, of my function T. Also, another thing here that I want to mention, the set of all V in V, right? The set of all vectors in my vector space V, such that T of V is W, is called the preimage of T. So this is what we call the preimage. And let me draw a picture so that everything will become clear. So we have here, let's say here is the vector space, let's say V. So this is the domain, right? And here I have an element, let's say V, little v in my domain. And this will go from, I will send this element through a map, let's say, right? or a function t, right, to this vector space here, W, which is the codomain. And here I'll have the element W, so this will be sent to this element W, right? And here, inside this codomain, I will have what we'll call the range. Right? And so this W is the codomain, and the function, this function will go from T from V to W. So we'll send, okay, let me do it like this. We'll send it here. Okay, now this is the picture. So you take an element and you send it from one world to another. It's like going from a, I don't know, let's say you're flying to California, today you're in Texas, and your application will be the plane, and the plane will map you from Texas to California. That's the same thing. Okay, now let's see some examples of these functions from a vector space to another vector space. For examples, at some point we'll want to call them linear transformations, but not yet. You will see that they have to satisfy a certain property. Okay, let's see some examples, and I will start with the, let's see, example one. And the example one that I have in mind is a function from R2 to R. For any vector, let's say V, and this time we said that the first vector space, let's say, let me write it and then I'll explain it, of V1 and V2 in R2, so in my first vector space, we define T from R2 to R. As you can see here, the first vector space is R2 and the second vector space is R. We define the T from R2 to R by the following. T of V1 and V2 will be equal to V1 minus V2 and V1 plus 2V2. Okay? And we're interested in the following. We want to find the image of the vector, let's say V, let's say -1, 2. We find the image of the origin. In other words, the image of the vector 0, 0. And the second one, the third one, let's find the pre-image. Find the pre-image of the vector V equals, no, let's say W. Let's stick with the notation of W, which is -1, 11. Okay. Now we want to use those definitions to find the image or the pre-image of a function from R2 to R. Well, the picture is quite clear if you look at the definition. By the way, can you hear me well? Is the internet okay? Because it tells me that the internet connection is unstable. So okay, so everything is fine. All right, that's good. Yeah, just let me know when something comes up. You know, I don't want to have any other surprises to record this lecture again and again and again. Yeah, you don't want to know how sad I was last night when after I recorded everything, and then I was like dead tired, and I wanted just to see the video so that I can upload it on YouTube and then just go to bed. And then when I saw there is no sound, I went, anyway. It's not like the worst thing that it can happen in life. There are worse things than this, so I should not complain that much. Okay, so let's go back to our problem. So we need to find the image of that vector v. So guess what are you going to do? You're just gonna replace v1 by -1 and v2 by 2. So for v -1, 2, we have t of -1, 2. This will be equal to, so as you can see, the way t of v1 and v2 is defined is v1 minus v2, so it will be -1 minus 2, and then the next one is -1 plus 2 times 2. So this will be -3, 3, right? Okay. Sorry, I made a mistake here. It's not from T, I was looking, it's from R2 to R2 because I have two components here, not from R2 to R, Jesus. All right. Anyway, I did not see it. So this is the image, so we can say that the image of the vector v -1, 2 is the vector -3, 3, and that's it. Okay? Let's see the second part, B. We want to find the image of the origin. So for V equals the vector 0, 0, we will have the following. We have that T of 0, 0 will be what? In this case, I'm just going to replace V1 and V2 by 0, both of them. So we'll have 0 minus 0, and the second one will be 0 plus 2 times 0. So in this case, you'll have 0, 0. So the image of the origin through the function t is nothing else than the origin itself. And now let's see the last one. Pay attention here, I need to find the pre-image of the vector w -1, 11. So in other words, if t of v, which is v1 minus, given by v1 minus v2, right? And v1 plus 2v2 is w, which is my vector is given -1 and 11, right? Then I need to determine v1 and v2. So in other words, I will determine the vector v. This will imply that, so then we'll have the following system, since we're equating the vector. So v1 minus v2 is -1, v1 plus 2v2 equals 11. This is a system with two equations, two variables. It's how many solutions do you think this system has? Two solutions, unique solution. So this system, let's call it S, will have a unique solution, a V1 and V2. That's one solution, right? S has a unique solution. Right? If you solve this, it's quite clear, and I'll leave it to you as an exercise to do it. You can use substitution, you can use elimination, you can use whatever you want, and this will give us the unique solution. V1 and V2 will be okay, 3 and 4 if I'm not mistaken, and that's the unique solution for this. In other words, we can say that, so the preimage of the vector W, negative 1, 11, is the set in R2, let's phrase it like this, consisting of the single vector V equals 3, 4. And that's it. That's the story of this problem. So I believe at this point it's quite easy how to find the image and the pre-image of a vector. Now I want to veer towards what we care about, and I want to define what is a linear transformation. So we'll talk about linear transformations. Okay. So let's start with the definition. Again, let's consider V and W two vector spaces. Let V and W be two vector spaces. The function, we say that the function T goes from V to W is a linear transformation of V into W when the following two properties are satisfied. When the following two properties are satisfied. This guy is giving me some headaches. The internet is telling me that the connection is unstable. Anyway, when the following two properties are satisfied, and these two properties, the first one is, in fact, is T of U plus V, what we call linearity, is T of U plus T of V for all U and V in V. And the second property, T of C times U, pay attention here, this C will be a scalar, will be C times T of U for all U in V, right? And any scalar, any real scalar C. So pay attention, C is a scalar here. Okay, so these are the two conditions that a function needs to satisfy so that it will become a linear transformation. I want you to look at them. They're very easy to, they're, I would say, common sense conditions. Another question is that we want to answer, what kind of functions are linear transformations? So what functions are linear transformations? So you want to answer this question. Are all the functions linear transformations? Well, you would be tempted to say yes, but not quite. You will be surprised that not all functions will satisfy these two conditions, although you might say that these are common sense conditions for me, but not quite. You will see that not many functions, you will see that there are functions which will not satisfy these two conditions. Okay. Let's see some examples. And let me go back to the previous example. So some examples. And our previous example was, let's look at this function, from R2 to R2. So T from R2 to R2, T of V1, V2 was V1 minus V2, V1 plus 2V2. Okay. This is a function. So what do you think? Do you think, what does your intuition tell you? Do you think this is a linear transformation or not? By just looking at it? So imagine, does this function here from R2 to R2 satisfy the two conditions over there? What do you think? Just intuitively.
Yes.
Yeah, most likely yes, right? Why not? So let's show that. So show that T is a linear transformation. And to show this, we need to verify these two conditions. So in other words, we take two vectors, let's say U and V, and we, let's say U of, so let's show this. We need to show that T preserves addition. T preserves vector addition and scalar multiplication. This is very important. This is, in other words, this is nothing else than just the two conditions. The first one is vector addition, right? It preserves the vector addition. Moves kind of slow. It preserves the vector addition, the first, which is the first condition, and the scalar multiplication, which is the second condition. Okay. Wow, it moves very slow. The internet connection is not the best. Okay. All right, so we need to show this. The first one, we want to show that T of U plus V is the same as T of U plus T of V. For all U and V, pay attention, these is our vectors in R2. Okay, let's do this. Let U be U1, U2, so we'll write this vector, and V is V1, V2. So these are the two vectors in R2. So B vectors in R2. And also, let's consider and let C be any real scalar, right? This is a scalar, it's a real number. Then let's see, what do we have? Then let's look at U plus V. U plus V will be, let's write them down. The first one is U1, U2 plus V1, V2. This will be U1 by the usual vector addition. This is U1 plus U2, comma, V1 plus V2. All right. And now let's see, T, who is T of U plus V? So T, I want to prove that T of U plus V is nothing else than T of U plus T of V. So T of U plus V will be T of U1, U2 plus V1, V2. But we have seen that the addition of these vectors will give us T of U1 plus U2, V1 plus V2. So far, this is just I haven't used anything so far. I just used the definition, that's it. And how to add two vectors. I haven't used the function, and pay attention, the function is defined in this way. T of V1, V2, it's defined like here, in this way. Is V1 minus V2 and V1 plus 2 V2. All right. Now let's use this. This will be equal to, so we said it's, pay attention, this is a new vector here. Let's say, let's call this is V1 prime, so that if you don't want to get yourself confused, and this is V2 prime. So T of V1 prime, V2 prime, we know how it is defined. So okay, let's write them. It is defined in the following way. It's, let me look again. So it's T of, it's V1 minus V2. So it's V1 prime minus, let's write them. V1 prime minus V2 prime, and V1 prime plus 2V2 prime. And now let's write them. So once we write this, we will have the following. So let's see. Here we have to pay attention a bit. So we will have that, this is, the first one is U1 plus U2 minus sorry, U1 plus V1, sorry. U1 plus V1, right? Minus U2 plus V2, right? And then the next one will be U1 plus V1, U1 plus V1, minus 2 times U2 plus V2. Okay. Right? But this is nothing else, if you want to write it, if we go further a bit, this is nothing else than just, let's write it like this, U1 minus U2, right? Plus V1 minus V2, okay? And the next one is U1 plus 2U2 plus v1 plus 2v2. Okay, wait. I think it's a minus here, sorry. Minus 2u2, and here it's a minus again. Minus 2v2. Okay. And this will be nothing else than just, this is nothing else than just, since we know who is our map T, this will be u1 minus u2, u1 plus 2u2 plus v1 minus v2, v1 plus 2v2, okay? So this will be nothing else than just T of u plus T of v. Anyway, you just have to look closely at them. So this is the first condition. So the vector addition. The second one is it will preserve, T will also preserve the scalar multiplication. So let's look at this first. So the C times U is C times U1, U2. And if we use the traditional operations of scalar multiplication and vectors, this will be nothing other than just CU1, CU2. So we have T of CU, this is nothing else than just T of CU1, CU2, and this will be C, since we know how the map T is defined, keep that in mind, so this will be CU1 minus CU2, and the second component will be CU1 plus 2 CU2. And guess what? This is nothing else. Now we take out the constant here, so it will be C times U1 minus U2, and U1 plus 2U2. Okay? And this is nothing else than just C times T of U. Indeed, this map T preserves the scalar multiplication. So from 1 and 2, we can conclude that T is a linear transformation. Okay. All right. Now let's see some examples of functions which are not linear transformations. And let me take another. So this is example. Okay, I did not number them. Let me take the following. F of x is sine of x. What do you think about this? And let's say this is defined from R to R. Let me take it like this. What do you think? Do you think this function is a linear transformation? What do you think? Some people say so you would be tempted to say no, correct? Why is that? Can you give me a reason why? Also, I encourage you to speak if you want. Also, the sine oscillates. Okay. That's a good intuition, yeah. Yeah, I understood, I understood. So sine oscillates, right? You wouldn't be tempted to say that it's a linear transformation. But now let me ask you specifically, which of the following two conditions sine will not satisfy? Does it satisfy the first one? Does this function f of x equals sine of x preserve addition? In other words, do we have f of x plus y? It won't preserve addition. Yes. Like Morgan says, it will not preserve addition. Okay, correct. The answer is no. Well, this doesn't hold true. In other words, sine of, let's say, x1 plus x2, keep in mind that we're from R to R, is not always equal to sine of x1 plus sine of x2. For example, you can cook up some x1 and x2. Let's take x1 to be pi over 2, let's say, and x2 to be pi over 3. And this gives us, let's look, sine of pi over 2 plus pi over 3. It is not the same as sine of pi over 2 plus sine of pi over 3. I think it's quite clear to see this, right? Okay. This was a bit well, it was easy, but not, you kind of had the intuition that this will not be a linear transformation. But now let me see another one, and something that looks easier than this. Let me take this. F of x is x squared. Let me take the simplest quadratic function, the parabola, right? F defined from R to R. What do you think? Is this a linear transformation or not? And if not, why? Why do you think this is not a linear transformation? Which of the two conditions will not be satisfied? The multiplication won't work because of the negatives. Let's see what people have to say here. Yes, correct. Addition doesn't work. That's correct. But you'd be surprised. Maybe scalar multiplication will work. Let's look. F of c times x is the same as c times f of x. Well, let's see. This guy is what? Is c squared x squared. And this is c times x squared. So it doesn't always work, like, right? But also, so this is it does not preserve the scalar multiplication. Preserve. But even more than that, even the vector addition is not preserved. In other words, f of, let's say, x plus y is not the same as f of x plus f of y. This guy, if you look here, is x plus y squared. And this guy is x squared plus y squared. And as far as I'm concerned, these are not equal as long as x and y are real numbers. So the vector addition, again, is not preserved. Okay, you see, it's a very simple function. Just took the parabola, and there you go. It's not a linear transformation. So f is not a linear transformation. All right. Now let me point out the remark. And the remark is the following. Two simple linear transformations are the zero transformation and the identity transformation Okay, let me write it. Okay. So the zero transformation is T of V equals 0, and T goes from V to W. So this is what we call the zero transformation, just like the zero function. Transformation. And the second one will be T of V equals V. T goes from V to W, and this is the identity transformation. So these are the transformations, and now I want to, so these are two examples of the null transformation or the zero transformation and the identity, just like for functions. And now I want to talk about, so the following theorem will address some properties. Will address exactly the issue of some properties of linear transformations. The properties of linear transformations. Let T be a linear transformation from V to W, where and we can where U and V are in V. So we'll consider two elements in V. Then the following properties are all true. Okay. So the following properties will hold true. The first one, T of 0 will always be 0. So when you have a linear transformation, that's it. It has to go. So when you evaluate at the origin, it must give you 0. The second one is T of negative V is negative T of V. The third one, if we want to see when we subtract two elements from that vector space, so when we have T of u minus v will be T of u minus T of v. Okay. And the fourth one, we can generalize the property. The first condition from the definition of a linear transformation, and we can write it like this. If we have this linear combination of vectors, let's say C1b1 plus C2b2 plus all the way Cn Vn, and we want to see how this will behave under T. So this will be nothing else than just C1 times T of V1 plus C2 times T of V2 plus all the way Cn times T of Vn. And this will hold true for all vectors. Let's say V1, V2, Vn in V. And any scalars C1, C2, Cn in R. So in the set of real numbers, so any real scalar. So I want you to look at these properties. So this will hold true. Now let's see some examples. The next example we will want to see is when we have a linear transformation and we know that some elements are mapped into some other elements, we want to find how is a certain element mapped under that linear transformation. So the example I have in mind is the following. Let T from, let's say, R3 to R3 be a linear transformation. So I'm giving you this information already, so you know what it means. Linear transformation. Okay. So T from R3 to R3 is a linear transformation such that T of 1, 0, 0. So it will send this element into 2, negative 1, and 4. T of 0, 1, 0. This will be sent into 1, 5, negative 2. And the last one, T of, as you can imagine, 0, 0, 1, will be sent into this vector, 0, 3, 1. And now we want to find T of, let's say, 2, 3, negative 2. Okay, I want you to look at it for a bit, for a couple of minutes. Let me just stand up a bit. My question to you is, does this ring a bell? Do you recognize something in here when you look at it? What vectors are we mapping here in R3? Do you recognize these vectors here? This one, and this one? Does this ring a bell to you? The identity, be more specific. Nope, not quite. What did we say about those three vectors in R3? We've said this before. They form what? I think we've said this before, and I said it in that last night in that video, that muted video. Do you remember, does the standard basis ring a bell to you? Remember when we said that any vector in R3 can be expressed as a linear combination of vectors in the standard basis? And the standard basis in R3, the standard basis in R3 is what? Will consist of this vector. Let's say E1, 1, 0, 0, E2, 0, 1, 0, and E3, 0, 0, 1. That's it. This is the standard basis in R3. Okay, so this is a very important piece of information, because when you look at this problem, you have to recognize this. You'll be like, ah, look at this guy. So he's giving me a linear transformation. He tells me I'm dealing with a linear transformation already. You have to think of this. It requires just a little bit of thinking of this problem. And you look that this linear transformation is mapping my vectors in the standard basis in R3 into some other vectors. But then you'll think that, wait a second, I already can express any vector in R3 as a linear combination of these vectors in the standard basis. Okay, great, since I know this, and then I have to find T of a certain vector, well, why not express that vector, which I'm interested in? In my case, it's the vector 2, 3, and -2 as a linear combination of those vectors in the standard base, and then I can apply I can apply T. So let's do this. So we have so let's write this. The vector 2, 3, -2. This can be expressed as a linear combination of vectors in the standard basis. It will be 2 times 1, 0, 0, plus 3 times 0, 1, 0, minus 2, sorry, 0, 0, 1. All right, great. This is, as you can see, this is my vector E1, this is my vector E2, and this is my vector E3. Great. Well, the only thing I need to do is just to apply T. This implies that then we have T of 2, 3, -2. It will be T of, and now I'm going to apply it to all of this here, 2 times yeah, all right, Aaron, no problem. I will add you. Just let me send me an email, please, that you are present, and I will add you manually afterwards. Okay. And this will be 2 times 1, 0, 0, plus 3, 0, 1, 0, minus 2 times 0, 0, 1. Okay. And now we will use the fact that T is a linear transformation, and we know that by using the fact that T is a linear transformation, let me write it here. In fact, let me write it like this. Transformation. Here we're here's where when the fact that T is a linear transformation comes into play. And this will be nothing other than just, so like I said, the linear transformation will preserve the scalar multiplication and vector addition. And this will give us 2 times t of 1, 0, 0, plus 3 times t of 0, 1, 0, minus 2 times t of 0, 0. All right, you already know which one is which one because this is given. You know that t of, well, if you look, this is t of 1, 0, 0 is 2, negative 1, 4. T of 0, 1, 0 is 1, 5, negative 2. And t of 0, 0, 1 is 0, 3, 1. Okay. All right, so we replace this. By the way, I think I'm going to have a request from you because I'm still, you know, with the attendance. I want to make sure that it's you behind the cameras. I think I will ask you to turn your cameras on for the last 20 minutes, 15, 20 minutes. So I would like you to do so, if you don't mind. So I'd like you to turn your cameras on, those of you who. So I want you, before I start taking the attendance, I want you to turn your cameras on so that I know it's you there. All right. So this is a linear transformation. We replace this, those of you who have a camera. This is nothing else than just 2 times 2, 1, negative 1, 4, plus 3 times 1, 5, negative 2, minus 2 times 0, 3, 1. Okay, and this is just a vector manipulation. You can do the computations, and I'll leave it to you as an exercise. But I think this will give us, I don't know, something like, according to my notes, 770. That's it. That's it. The only thing you need to see here is that that the fact that any vector can be expressed as a linear combination of vectors in the standard basis. That's the thing you need to see at this problem. All right, now let me see another example. And this time I'll define a linear transformation using a matrix. Let's see another example. Do you have any questions regarding this example? Is it clear for everybody? Is it clear?
Yes, sir.
All right, great. I'm glad to hear that. By the way, please stop me at any time when you don't understand something. So, because I would like to have this kind of interaction with you. I don't like to talk by myself. That's why I don't like to film videos with just me talking in front of a camera. I'm not a big fan of that. All right, let's see another example. And now let's define the function t from R2 to R3 as the following. T of v, and I want you to pay attention here, will be AV. So I will take a matrix and I'll apply to, I think somebody has its mic on. Yeah, I'll definitely would like to, you guys have the mic turned off. I can tell you, I'll tell you that. This will be 3, 0, 2, 1, negative 1, negative 2. And I will apply this to this vector, v1, v2. It will look like this. And what I'm interested in finding here is the following. Find t of v when my vector v is given by 2 and -1. Another thing that I'm interested in is to show that T is a linear transformation. In fact, all maps that look like this, when you have, are linear transformations. So in this case, show that this is a linear transformation from R2 to R3. Okay, so let's do this. The first part is quite easy. The only thing you need to do, so for my vector v equals 2, -1, let's say, right? We'll have that that T of v, which is AV, will be nothing else than just, we're going to take this matrix, as you see it here above, 3, 0, 2, 1, -1, -2, 3, 0, 2, 1, -1, -2, and we will apply it to my vector v, which in my case is, so v1 will be 2, v2 will be -1, so this will be 2, -1. And once you do this multiplication, keep in mind, or it's like the usual matrix multiplication, right? This will give us, the multiplication will be a column vector. And this will give us 6, 3, and 0. Keep in mind, this is a vector in R2. And what we have obtained by multiplying the to that matrix will, has like 3 rows, 2 columns, right? 3 by 2, and this is 2 by 1. So we will obtain 3 by 1, a vector in R3. Right? So as you can see, the map is defined from R2. So we take an element in R2 and we will obtain an element in R3, which means that, so this means that, which means that T of 2, -1 will be nothing else than just 6, 3, 0. All right, and that's it. Now to see that this is a linear transformation, well, it's obvious to see. So T is a linear transformation. Why is that? It doesn't matter which matrix you're going to take there. You can put any matrix. In general, you'll have, you have to show that, for example, the first condition was to show that T of u plus v is nothing else than T of u plus T of v, right? But T of u plus v is A of u plus v, and this guy is nothing else than A of u, and this guy is A of v, which again, it's easy to see. And the second one is if we consider for any vector u in R2, u in R2, and any scalar C, let's say a real number, any real scalar, we will have that T of C times U, it will be, well, it's A of CU, and since this is a scalar, this will be C times U, A of U, which is C times T of U. And again, this holds true. You see that we haven't used anywhere here the fact that By the way, somebody has its mic on, and I can hear. Who is that? Okay. As you can see here, I haven't used the fact that the fact that the matrix is given in a certain way. So, in other words, we will have the following theorem. And this theorem will concern the linear transformation given by a matrix. Given by a matrix. Philip, I think your microphone is on. Philip, I think your mic is on.
How's your workout going? Yeah, get started yet? You know what's starting tomorrow. Tomorrow, he can start tomorrow. There is no tomorrow.
Philip, can you turn your mic off?
That's good enough. It's like going to church on Sundays, you just watch it on TV. So
Oh my goodness. All right, so we let A be.
It's like church on Sundays. Just watch television.
How bad on church on mattress?
Yeah. We had this one girl, she would come in there when I worked at her free. Every Sunday she didn't have a babysitter, or her mom was.
Yeah, I think I can mute him. Let me find him.
So she would always bring her kids to work, you know, and she would sit up in the break. Okay, baby, so this here. Y'all watch church from here and everything. Just put on TV as the kids were watching, and it was funny that there was that stuff with that.
Philip, can you mute your microphone? I know.
He's like, come on, the mom couldn't even, the grandma couldn't even take him there. They were watching on TV.
I don't understand why I cannot mute him.
I think I start tomorrow, right? Well, but my trainer said no. She yells at me.
Wait, something is going on here. I cannot mute him. I don't understand why. Anyway. All right, so let A be an m by n matrix. The function anyway, the function t defined by t of v equals AV. So just like I said, for any matrix A, is a linear transformation from Rn into Rm. So in other words, we will have something like this. So we have the AV, which will look, I will just write the matrix A11, A12, A1n, A21, A22, A2n, AM1, AM2, AMN. And if we multiply this by the vector V1, V2, Vn, so this is a vector in Rn. Once we multiply this, right, by the usual multiplication, you will get that A11 times V1, A12 V2 plus all the way to A1n times Vn. Then the second one will be A21 times V1 plus A22 times V2 plus all the way to A2n times Vn. And this is AM1 times V1 plus AM2 times V2 plus Mn times Vn here, okay? So this is, in other words, this is nothing else than just a vector in Rm, right? So this is a linear transformation no matter the matrix. Okay, guys, I think I'm gonna stop here. Let me take the attendance.